When a loaded bulk carrier receives a full astern order at sea speed, the distance it travels before stopping can exceed 3 kilometers. That's 15 ship lengths. The engine responds. The propeller reverses. A stern thrust develops exactly as designed. And the vessel continues moving forward anyway, not for seconds, but for minutes. Nothing is broken. This is how momentum works at scale. On this 100,000-ton ship, you're standing on the bridge conducting a controlled crash stop test in open water. The ship is loaded, moving at steady speed through deep ocean, powered by a single massive fixed-pitch propeller driven by a reversible low-speed diesel engine. There's no brake pedal. No friction clamps grip the shaft to halt the vessel the way disc brakes stop a truck. The anchor isn't designed for emergency stops at speed, and the rudder doesn't eliminate forward motion. When the order is given, the ship stops by changing the forces acting on it. First, a head propulsion is withdrawn. Then the machinery generates thrust in the opposite direction. Throughout the process, water resists the hull and absorbs the energy the engine spent hours building into the ship's motion. The real question isn't whether a ship this size can stop, it's how much ocean disappears before physics catches up to the command. Before anyone touches the controls, the ship's mass and speed have already determined the answer. A moving ship carries momentum, and its kinetic energy rises sharply with velocity. At the same displacement, doubling speed doubles momentum but quadruples kinetic energy. That energy can't simply vanish. It converts into turbulence, propeller wash, heat, disturbed water, and the vessel's changing motion. The hull helps. Water resistance slows the ship even when propulsion stops. A large commercial vessel can coast for a surprising distance, but it's far from frictionless. The bow pushes water aside. The wetted hull drags against the sea. Waves form along the waterline. Appendages disrupt flow. At higher speeds, resistance grows stronger. As the ship slows, resistance weakens, which creates a frustrating effect. The first few knots bleed away faster than the final ones. In practice, stopping the engine and stopping the ship are not the same thing. If the bridge simply cuts propulsion, the vessel begins coasting. This works when sea room is abundant. It's efficient, gentle on machinery, and predictable when planned well ahead. Most real stops happen far earlier and look much less dramatic. On approach to port, the bridge reduces from sea speed in stages. Engine load decreases, the vessel is allowed to slow, and the next command is timed based on known response. The best stop is often the one planned so early that no one needs full astern at all. That's why expert ship handling looks slow from shore. While the harbor still seems distant, a large ship may already be surrendering speed. The bridge is deliberately spending sea room, converting momentum into water disturbance before reaching a point where low speed is required. A crash stop removes that luxury. It asks machinery and hydrodynamics to produce maximum deceleration when the ship has already built significant energy. It's a useful test of system performance, but it's no substitute for planning. In that test, the ship can't rely on drag alone. The propeller has to become an active opponent to the motion it created. The test begins with the ship in position. The captain and bridge team confirm sea room is clear. Position, heading, speed, weather, draft, and loading condition are recorded, because stopping performance is meaningless without the variables that shape it. Then, the order is given. Full astern. On the bridge, the command is immediate. The physical response is not. The engine telegraph or propulsion control transmits the order to the machinery system. The officer of the watch monitors speed and track. A stopping vessel doesn't always travel perfectly straight, so the captain watches heading. The rudder remains effective, but its behavior will change as water flow around the stern shifts. The bridge marks the position where the order was given. How quickly does a head thrust disappear? How long before a stern thrust begins? How much distance passes during the transition? Does the ship veer to one side? What happens to steering as speed falls? The answers become part of the ship's operational knowledge. Recorded stopping characteristics, time, distance, track shape, engine response, behavior under different loading, give future navigators a baseline for real decisions. The test isn't just proving the ship can stop on command, it's defining what stop actually means for this hull, this machinery, this displacement. Below, that meaning is being constructed one shaft revolution at a time. In many large commercial ships with fixed-pitch propellers, the blades can't rotate into a reverse thrust position while the shaft continues turning forward. Their angle is cast into the metal. To produce a stern thrust, the entire propulsion system must reverse its rotational direction. On this vessel, the propeller is driven directly by a reversible low-speed two-stroke diesel. A head power is cut. Before a stern rotation can begin, the engine and shaft must depart their ahead-running state. The ship is still moving forward. Water is still flowing past the hull and into the propeller disc. That flow affects the shaft. The engine control system manages the transition within the machinery's operational limits. Then starting air. High-pressure compressed air, stored specifically to start a massive diesel, initiates rotation in the astern direction. Once the engine establishes proper firing sequence, fuel takes over. Now the same propeller is turning the opposite way. Its function has reversed. Instead of accelerating water astern to push the ship ahead, it generates thrust to resist the ship's forward motion. The bridge gave the full astern order minutes ago. Only now is real astern thrust reaching the water. That delay is one reason stopping distance stretches so far. The chief engineer is also watching something the bridge may not see: the machinery's capacity to respond to repeated maneuvering commands. Large diesels rely on stored compressed air for starting, and maneuvering data can include limits on consecutive starts, minimum operating revolutions, and astern operation constraints. Repeated ahead-stop astern sequences aren't free. They consume starting air and impose transient loads on machinery that may have run continuously at sea for days. During normal maneuvering, engineers leave margin for the next command. During an emergency stop, they must protect the machinery while delivering the response the bridge requires. A stopped engine is worthless if the next critical start fails. Other ships use different systems. A controllable pitch propeller can change blade angle while the shaft continues rotating in the same direction, producing a stern thrust without reversing the engine. Some vessels use geared propulsion, electric drive, potted units, or multiple screws. The machinery changes, the physics does not. Forward momentum still requires opposition. Energy still transfers somewhere. Water remains the medium through which most stopping force reaches the hull. The stern begins to feel different first. The propeller is working astern while the ship still moves ahead. Water approaching the blades passes through a flow field shaped by the forward-moving hull, while the propeller attempts to generate thrust against that motion. Flow becomes far more disrupted than during steady propulsion. The engineering watch monitors temperatures, pressures, starting air reserves, control signals, and machinery response. The chief engineer doesn't eliminate risk. The job is confirming the propulsion demand is met and the plant can sustain it. On the bridge, speed begins falling more sharply, but the vessel may develop sideways motion or a heading change. Propeller side force, rudder flow, wind, sea state, trim, and hull shape all influence the track. A crash stop is therefore measured along the path the ship actually follows, not as a single straight line projected from the bow. This is why the formal term is track reach. The distance traveled along the vessel's actual path from the moment full astern is ordered until the ship comes to rest. For ships subject to IMO maneuverability standards, the normal requirement is expressed in ship lengths. Under specified full astern trial conditions, track reach shall not exceed 15 ship lengths and no more than 20 for certain large displacement vessels if the administration considers 15 impractical. For a 200-meter bulk carrier, 15 ship lengths equals 3 kilometers. Those figures sound enormous because the physics is enormous, but they're testing and design criteria under controlled conditions. They're not guarantees for real emergencies. Wind changes the track. Current alters motion over ground. Shallow water changes hydrodynamic behavior. Loading and trim affect the hull. Machinery condition affects response. Initial speed determines how much energy must be removed, and human reaction time passes before the system even receives the command. The lesson is simple. Full astern is not an instant result. It's a process. Halfway through the stop, one expectation begins to fail. You might assume the ship becomes easier to control as speed drops. Often, the problem just changes shape. The rudder doesn't turn the vessel simply because the bridge moves a wheel. It works by deflecting water flow across a shaped surface to create force. Change that flow, and rudder authority changes with it. During a head propulsion, strong flow exists around the stern and rudder. During a stern operation, that pattern is reorganized. At low forward speed with the propeller running astern, the vessel can have weaker or less predictable steering, even though it carries far less kinetic energy than at the start. The captain is now watching two separate problems: stopping distance and directional control. They're related, but they're not the same. That distinction matters in a real emergency. The shortest theoretical stop isn't automatically the safest collision avoidance maneuver. Turning early may create more separation than attempting a straight-ahead stop. In another geometry, a turn introduces new danger. The captain and officer of the watch work with actual traffic geometry, collision regulations, available depth, sea room, machinery state, and this particular ship's known characteristics. There is no universal command that solves every situation. The bridge chooses among imperfect tools: course, speed, engine power, rudder, available water, and time. The full Astern stopping test exists partly so those decisions aren't based on intuition alone. The ship continues slowing. 10 knots becomes 8. 8 becomes 5. The stern wash remains violent. The vessel carries far less energy now, but the final portion of the stop still refuses to happen instantly. As speed falls, hull resistance, which helped at the beginning, also weakens. A stern thrust now carries more of the load. Long before a real emergency, the ship provides its officers with answers. The maneuvering booklet contains performance information specific to that vessel. Stopping trials and calculated data show how it behaves from different ahead speeds, in loaded and ballast conditions, under different engine settings. The information includes time, track reach, head reach, lateral drift, engine revolutions, and speed progression. The bridge may also display maneuvering data for quick reference during port approach or confined water navigation. Those figures aren't guarantees. They're baselines. Change the vessel's draft, expose it to strong wind, operate in shallow water, alter its trim, or introduce a machinery limitation, and real behavior diverges. This is where the human layer becomes more important than the diagram. Suppose an obstruction appears ahead while the vessel still carries sea speed. The captain can't simply ask, "What's the stopping distance of a 100,000-ton ship?" That question is too vague. What is the current speed? What is the present displacement and draft? What propulsion arrangement is available? How much clear water remains ahead? What traffic will be affected by a turn? How quickly can a stern thrust actually develop? What did this ship do during trials? And is stopping even the best way to avoid the danger? Those are ship handling questions. The answer may be full astern. It may be an early course change. It may require both. What matters is that the decision must be made before the ship's response becomes visually obvious. Because once a vessel this large proves the previous decision came too late, the proof arrives as distance already spent. Bow thrusters, tugs, and anchors are powerful tools, but they're not substitutes for propulsion-based stopping at sea speed. Thrusters are low-speed maneuvering devices. Tugs provide large external forces when properly connected and deployed. Anchors are holding equipment, not highway brakes. Normal ship handling doesn't treat dropping an anchor from full speed as equivalent to stamping on a pedal. The safest stopping system isn't one piece of machinery. It's the planned relationship between propulsion, hydrodynamics, sea room, and people who understand the gap between command and result. On the test ship, that gap is nearly closed. The speed display approaches zero. Astern thrust is reduced before the vessel begins accelerating backward. The stopping position is marked. Time is recorded. The track shows exactly where the ship traveled after the order was given. The test is complete, but the useful product isn't the spectacle of a massive ship sitting motionless in open water. It's the knowledge created by the maneuver. The bridge now has evidence for future planning. Engineers know how the propulsion plant behaved through the transition. The ship's stopping characteristics can be compared with applicable standards and made available to navigators who may later need to judge real sea room under far less controlled conditions. That is how a 100,000-ton ship stops. Not by finding friction strong enough to clamp the hull in place, by withdrawing a head thrust, using the ocean's resistance, producing a stern thrust through the propeller, and beginning the entire sequence while enough water remains for physics to finish the job. On land, braking is something a machine does after the driver decides to stop. At sea, the decision itself is part of the system, because by the time a ship this size visibly begins to slow, the outcome has already been determined by the ocean it crossed, while the command made its way from the bridge to the water.